If you ask a physicist what the world is made of, they will describe a microscopic Russian nesting doll. Everyday objects are made of atoms. Atoms contain protons and electrons. Protons are made of quarks. At the very bottom, we assume reality is built out of these tiny, indivisible physical particles, bouncing around like microscopic billiard balls. This standard model of physics is incredibly precise. It predicts the behavior of subatomic particles with enough accuracy to measure the distance between New York and Los Angeles to within the width of a human hair. But even with that precision, the math hits a wall. Physics can perfectly predict what particles will do, but it cannot explain why they have the specific traits they do. For example, every single electron in the universe has the exact same mass, not approximately the same, but exactly. This diagram highlights the problem. Those empty gaps represent the roughly 25 fundamental constants of the universe. Because physicists cannot mathematically derive particle mass from deeper logic, they are treated as manual inputs, numbers we measure and plug into equations to make them work. This blind spot suggests we might be looking at the problem from the wrong level. It raises the possibility that particles aren't the fundamental starting point we've assumed them to be. When the core properties of matter must be measured rather than calculated, it suggests that the things we call particles are the result of a deeper process we have yet to map. We can find a clue to that process in a laboratory study called cymatics, the observation of visible sound patterns. When you apply specific acoustic frequencies to a metal plate covered in random sand, the grains organize themselves instantly. The invisible vibration forces the sand into a symmetric mandala. This provides a new way to visualize the quantum scale. An electron could be viewed as a localized pattern of vibration within a deeper underlying field. In this model, what we measure as mass is the specific geometric shape of that vibration. If the frequency or the pattern changes, the particle's measurable traits change with it. This shifts the focus from stuff to structure. The geometry of the oscillation dictates the form of the matter we observe. This concept is explored in Williams' dynamic theory. It takes the laws of thermodynamics, the physics of heat and energy, and applies them to a generalized geometric framework. Williams found that by starting with these geometric principles, rules like the speed of light and the relationship between mass and energy, E equals mc squared, emerge from the mathematics naturally, rather than being assumed as starting points. A separate framework called Oscillatory Dynamics, or ODTBT, proposes that our four-dimensional reality is a projection of a 12-dimensional geometric structure. As this diagram shows, it's similar to a complex object casting a simplified 2D shadow. This framework calculates particle mass ratios directly from the geometry. These derivations match real-world measurements to several decimal places, providing a mathematical path to those 25 constants that standard physics can only measure. These two frameworks were developed independently using different methods, yet both conclude that the properties of particles are the measurable output of an underlying geometric pattern. The math suggests these physical constants are not arbitrary. They are the fixed geometric consequences of a deeper multidimensional structure. This research is still at the frontier. Both frameworks currently share the same gap. Neither has fully derived the Born rule, the specific math that governs probability in quantum mechanics. These ideas remain outside the mainstream. Because they challenge the standard model's core assumptions, the research requires rigorous documentation and testing to meet the high burden of proof required for such a shift in perspective. If these models are verified, gravity and electromagnetism and quantum effects would be unified under a single geometric system. Large-scale mysteries like dark matter might turn out to be artifacts of this interconnected structure, signatures of the geometry we have misidentified by looking at the universe from the wrong scale. A moment of wonder. This research envisions a reality defined by an invisible geometric song, where every particle in the universe is the shape left behind by the vibration.